All right. So, hello everyone, and first, great thanks to the organizer for this nice event. I'm Johan Henaff. I work at Laboratoire Kessler-Brussels in Paris. I'm in the multimode quantum optic groups with Mathieu that talked yesterday. And so, today we'll talk about the first approach to reservoir computing and toward quantum protocols. And so, in the first place, I will talk about what is reservoir computing, and then I'll talk a bit about how we want to make it quantum. So first, what is reservoir computing? So you're probably all familiar with neural networks. Artificial neural networks became like very popular in the last decades. So just a quick reminder, here you have the general structure of a neural network. You have an input layer, which is connected to a hidden port. Within this hidden section, you have several layers, all connected, and these layers are all connected together. And the last layer of this last section is connected to an output layer. And so usually what you do is that you send information at the input, you gather them at the output, and then you train all the links in your system to try to predict as well as possible the expected output. So this kind of protocol are very nice because they are very efficient. The main drawback is that they are very resource intensive to train because you need to train all these links. And so to tackle this problem, what you can do is go to reservoir computing. So here you have the general layout of reservoir computing. You have the same general structure with an input layer, an hidden layer, and an output layer. But this time you will have like random and fixed links between the input and the reservoir. Within the reservoir, you have like nodes randomly connected together with like random weight also on these links. This is why we call it the reservoir, because we have all this collection of nodes. And then you have the output layer. You have also random links, but this time we'll train these links. And so this kind of setup is, of course, as you can imagine, less versatile than the typical scheme of artificial neural network. But as you only train the last layer, it's much more faster and easy to train. So in our case, we used a specific type of reservoir computing called delayed feedback reservoir computing. In this setup, so you have the same structure as reservoir computing, the classical reservoir computing. But this time, instead of having random connection of nodes in the reservoir, you have a time demultiplexed reservoir. And so you end up with this loop-shape structure. And so, like in the general setup, you have input data that will be linked to every node in the reservoir. And you will only train the links between the nodes of the reservoir and the output. For this kind of setup to work, you need two main ingredients. The first one is some non-linearity somewhere. And the second one is some memory. So, for the memory, for the non-linearity part, I will come to it later when showing you the experimental setup. And for the memory, as I said, it's a time demultiplex reservoir. The nodes are time demultiplexed, and so you have some short-term internal memory built within the structure of the system. And so, to have your memory, you just need to create these links between the nodes. And to create these links, you have two means to do that. You can use the limited bandwidth of your detection system. So basically, when you read the node at time step n, you're still in the Trojan state induced by the node at time step n-1. And so the information in the node at n-1 will be carried out to the node at time step n. So this is the first mean, and the second thing you can do is just have a feedback. So you will inject the data of a given node back with the information you are encoding in the new node. And so, okay, this is the two main way of creating memory and links in your reservoir. So now, as I said, let's get to the experimental setup. So here is the experimental setup. So it's a very simple one. Basically, what you have is that to create our node, we have a pulse laser at 156 megahertz. And so each pulse of this laser will be a node of our reservoir. And so the data will be encoded in the phase of the pulses, thanks to an electro-optical modulator. To create the links between the input layer and the reservoir, we apply a random mask on each input data. And then each input data will be mapped into each node of the reservoir with this random link. Then, to measure the value that were encoded in this node, we perform a homodyne detection. And this is where our nonlinearity that I talked about before come from, because the homodyne detection will not give you just the phase of the node, but the sinus of the phase of the node. And so this nonlinearity is enough for us to make reservoir computing work. And so, now we have our, and lastly, so after our homodyne detection, we just take one part to record the values of the node, and the other part, we feed it back to the system with this long delay line, which will be our loop, and we mix them with the new input data, and so this is our feedback. And so, the training is very simple. Basically what you do is you send a bunch of input data in the system, you record all the nodes value with your homodyne detection, and then what you want to do is to determine the matrix W out that will connect the node of your reservoir with your output. And so to do that, you just perform a simple linear regression between the nodes of the system, the values of the pulses, and the expected output. And then when you want to try on unknown data, you just send a bunch of unknown input in the reservoir, you measure the values of the node, and then you multiply the values of these nodes by the matrix W that you determined before. So in the end, it all came up to just basic linear algebra. So this is our setup. Now let's see how it performed. So this is some results. What you have here is that former PhD student in our lab showed that the noise of our various parameters of a laser is correlated to the noise of the pump. So if you want to measure all this noise at the same time, it's very complicated. It's a huge setup that draws a lot of energy from your laser. And so what we would like to do is to predict these various noises just by measuring the noise of the pump, as we know they are correlated. And so we used as the input of our protocol the noise of this pump laser, and with that we try to predict the noise of the power fluctuation or the central frequency fluctuation. And with that you can imagine some setup where you actively correct this fluctuation just by measuring the noise of the pump. And so here are the results. As you can see, so okay, the error looks big, like 0.4, but maybe the function we use to calculate the error is not the fittest here. What just you can notice is that like the prediction, which are the dashed line, follows quite well the real noise, which are the solid line, the solid colored line. So okay. Now that we have a classical setup, we would like to go quantum. And how to go quantum? We are working with a team of theoreticians at IFSIC in Palma de Mallorca. And so what they show is that if you take a general scheme of reservoir computing and you replace the coherent states by squeeze states, you greatly increase the computational capacity. It's what you can see on the chart here. So I won't get into the detail of what this computational capacity is. What you need to know is that the bigger the bar and the more colorful it is, the better it is. And so on the far right, you have the encoding in the phase of a squeezed vacuum. And in arg alpha, you have the encoding in the phase of a coherent state. As you can see, just replacing your coherent state by squeeze states should improve your computational capacity. Okay, so now I will come to this quantum state. So I said we need squeeze light to improve our system. And now I will just make a quick introduction to what is squeeze light. So yesterday, Mattia talked about the continuous variable systems, and so you already had a quick introduction, but I will talk to it again. So the electric field operator, it can be decomposed into these two quadrature, X and P, and these two quadrature don't commute, so you have an Heisenberg uncertainty that prevails here. And so what we would like to do, what are squeeze states? Squeeze states is just reducing the uncertainty along one of the quadrature at the expense of increasing the uncertainty along the other. And so you can link this squeeze state to a PR state by just a simple basis change. And this basis change can be implemented via a simple beam splitter operation. Okay. And so experimentally, how do we generate our squeeze states? So you send a high frequency, beam into a nonlinear crystal. It will generate like two beam at lower frequency. So you have energy conservation, momentum conservation, and so these two photons will be entangled. And by performing a basis change, you go from entanglement to squeeze states. So in our case, we have pulse light. So in the frequency domain, we end up with a frequency comb. And so each tooth of our frequency comb will generate a pair of entangled teeth at the output. And so if you perform a basis change, you end up with a multimode squeezed Hamiltonian, multimode squeezing Hamiltonian. And so that's it. That is what we are trying to do. And so experimentally, this is how it looks. So we have our pulse laser. We use the second harmonic crystal to generate our pump beam. And then we pumped it into a PPKTP waveguide. So if you're a bit familiar with squeezing experiments, you know that most people use OPO cavity. But in our case, we want to have a pulse squeeze light. And so if you use an OPO cavity, you will like filter out the pulse nature of your laser. And so we can't use this cavity. So instead we use a nonlinear waveguide to maximize the nonlinear interaction. And with that we now are squeezing. And so then we just perform a homodynamic measurement. With that, on the local oscillator we implemented a pulse shaper to shape the spectrum of our local oscillator to measure the squeezing along the various frequency mode. And on the right you can see the various amount of squeezing along the various modes of our pulses. And so if you're a bit familiar with squeezing, you can notice that we don't have much of it. So 0.5 dB at most on the first frequency mode, which is quite low because our waveguides are far from perfect. There is a lot of room for improvement. And we can't use cavity, we can't reach like the large amount of squeezing that other team can. So that's it. That is how we are generating our squeeze states that we would like to implement in reservoir computing. But now it's still, so with the team of theoreticians we are working with, it's still unclear what kind of protocol we should implement now. So we are also working on creating a more complex reservoir structure. And so to do that, we use the principle I just talked to you about earlier. By sending two squeeze states into a beam splitter, you end up with entangled states. And so we have multimode squeeze states, so you end up with a multimode entanglement at the output. And what you can do is repeat the operation with a delay on one of the arms. And with that, you will have like a dual cluster rail entanglement with this very complex entanglement structure. And with that, you would like to develop like a complex reservoir computing protocols. Okay, so this is it about my work. So now I would like to come a bit about the topic of this workshop, and so I would like to talk a bit about continuous variable protocols and energy. So here, first, I put a photo of our experiment, at least a part of it. So in the first place, what I would like you to notice, especially the theoretician in the room, is that when you just have two squeezers and a beam splitters, it ends up with like 300 optics. So please be gentle with us when you're drawing your models. And the second thing I would like you to notice is that in our experiment, we do not have cryo, or we do not need to cool anything. We are at room temperature. And so this is a very nice feature when you want to save on energy. And also, with a continuous variable system, it is quite easy to scale up the system. Like for instance, when you have a superconducting qubit, it's very costly to add one more qubit. But in a continuous variable system, I mean, photons usually come in great numbers, and so once you have a setup that works, you can like add more nodes at the burst rate of your laser. So yeah, that's why I mean I think CV can be a very nice thing for energy initiative. And now I would like to talk about something maybe a bit off topic. So far we mostly talked about solutions we scientists are building to help reducing energy consumption through quantum technology. And on Tuesday we had a great talk about the rebound effect by Jan Goetz, and it made me wish to talk about something a bit off topic. So my point is that if you want to make improvement about energy consumption and stuff, you shouldn't have a strict border between science and politics, because I mean it may be, I mean, the technology we are developing may be or may not become very powerful. It may be used in many ways, some good, some not so good, and you can't expect society to know what to do with it. You can't expect society to come ask you what they should have done with it, and most of all, you can't expect JP Morgan, Exxon, or Société Générale to not extract more oil or make more profit on markets with it. And so, because I mean, you can be sure that these companies will be much faster to handle these technologies than the rest of society and our politics. And you can't say, oh, I mean, too bad, scientists can't do anything about it, or this is in the hand of scientists, and this in the hand of society and politics, and I mean, whatever, it's not our problem. So no one but this community can know better than anyone else what are the potential consequences of what we are doing. And if you want to avoid like some rebound effect, for instance, you have to do something about it and not just hope that the world will avoid it by itself. And so maybe it's a bit too much, but I would like to talk about this this quote from Rabelais, which says, "Science without conscience is the ruin of the soul." And so, if you are willing to like prevent things, you need to do something. Like in the 20th century, physicists and engineers, some of them were deeply involved into politics, and they tried to steer where the technology should go. And I think if you want to improve society with the technology we are doing, it's something we should do too. So, with that, thank you very much. This is my team, a picture that you already saw yesterday. And a special shout out to my PhD supervisor, Valentina Parigi, and the two people who work with me on the experiment, Francesca Sansavini and Iris Paparelle. Thank you very much.
Questions?
Thank you very much for interesting talk. So basically, that what you have talked about was, as I understand, is also all about the Gaussian operation and Gaussian input states, right? Isn't it? So to harness the quantum computational advantage, so I think that maybe this non-Gaussian operation or input should be necessarily. So can you comment on some necessity of this non-Gaussianity, or if we have any plans how you are going to implement that?
Yeah, so you're absolutely right. So everything I showed you is purely Gaussian. And indeed, if you want to have to attain a quantum advantage, you need some non-Gaussianity. So currently, we are not planning in the near term to implement non-Gaussianity, but it's something that we are considering. There is another experiment a bit similar than ours, to ours, in our lab, where they are trying to implement non-Gaussianity. And so yeah, our point here is that we want to see if introducing quantum states, so squeezing, just for a first step, improve our computational capacity. And after this first step, maybe we will consider like subtracting photons or stuff like that to create some non-Gaussianity in our system.
I do have another question. You were mentioning that CV can be helpful for energy consumption. However, in the preliminary study that I showed, I said at some point that there's a lot of classical post-processing costs associated to CV stuff, at least in the case of QKG. I wanted to know your opinion on that and if you have started to estimate this.
Yeah, so you're absolutely right. So I didn't went as far in the calculation as you did, of course. Okay, so it would need like a bigger investigation. Yeah, you're probably right that every post-processing stuff may cost a lot of energy. The thing is that, I mean, a cryo like draws a lot of energy, and so maybe if you can just avoid using one, would be just a nice step. Then you will need to do a full investigation on it to make sure that it's efficient. But yeah, I think it's CV is still a nice thing.
Okay, let's thank the speaker, and then trying to figure out who's the next speaker.